Anyway, welcome along. I'm absolutely delighted to introduce Tom. Tom has been giving lectures for almost 30 years, so I reckon he'll be pretty good by this time round. He lectured me almost 30 years ago. He was one of my, in fact, probably my favourite lecturer, apart from all the other ones, but he was a particularly effective one. I can nearly remember some of the fluids, but I'm sure this evening you're all going to get, if you're not going to get a face full of water, you will get an earful of fluids. The title is fantastic, Violent Waves, so hopefully there was some violent waving at the end in appreciation. But Tom's going to tell you a good bit about his research that involves trying to avoid people getting wet or drowning at the coast. It's an area he's been deeply involved in. He's even managed not to blind himself using lasers in the fluids lab, which is quite a result. But he's been obviously around for a long time. This inaugural has taken quite a while to arrange. You've only been a professor for a while, but like many others, we are making up for it now. So when he's not lecturing and getting wet, Tom is our Dean International. So he's one of the people who are helping Edinburgh make sure that we bring in a wide diversity of students from all around the world, and long may that continue. So without further ado, I will not mention his football club at all, and I'll move swiftly to Tom. Good luck.
Thank you very much. Thank you very much, Gareth. Thank you very much, Ian. Only a university could conceive an organogram with two solid lines upwards, so my two bosses, so I have to be very nice to you both. Thank you all very, very much for taking time out of your evening to come here and take part. I did advise you to come an hour later and just skip the lecture and come to the drinks, but you've come, so you're stuck here now. Yes, it is a little bit late, but hopefully it'll be worth waiting for. I'm going to try and stick to the 1 hour. It's been stubbornly an hour and 5 minutes in practice. One of our two wonderful daughters, both of whom are interested in theatre, said that lots of times they've been rehearsing and it's taken an hour and a half, but when they get it right, it takes only an hour. So hopefully if I get it right, it will only take an hour this afternoon. Okay, so that was a bit of fun up here. Let's see if we'll come and get the answers to what you think should be the facets of a good inaugural in a few minutes. I should say that photograph in the middle at the top there has been out and about for many, many years. It was taken by a colleague at HR Wallingford, George Motica. We thought it was very beautiful. We do believe it's Hartlepool in northeast England. We believe that the person seen there was not a coastal scientist looking at a safe distance, but had been smoking some things that he or she really should not have been smoking. So it's not quite as romantically beautiful as it looks, unfortunately, but there we go. Right, let's see if we can make this all work. Acknowledgements. This is in alphabetical order, but as it happens, the very first person on there is very keen on acknowledgements, and quite rightly so. So I've been brought up to make sure the acknowledgements are right up front, top dead center, because this journey has only been a collaborative one. My contributions have been pretty small, but I've been very lucky to be in fantastic teams, and so this is a huge collaborative adventure. Said William Alsop will, if there are no acknowledgement slides in a presentation, ask the presenter if they'd done it all themselves. And give a similar response in the review of journal papers. So I'm absolutely delighted that so many names up there. It really, really reflects the way in which I like to work. Maybe I'm not that inspired myself. I need to work with other people. So if your name's not up there and you think it should, I'm really, really sorry. But this is also a product of having worked in large collaborative projects, European Commission Framework 6 and Framework 7 projects over the years. And there's very few advantages of getting older, but one of the advantages of getting older is seeing the people that you worked with as postgraduate researchers become academics, and the academics become senior academics and professors. And so we have this incredible bond of trust, actually, because we all started out together as postgraduate students, so we completely trust each other. So those names there, I won't do PowerPoint karaoke, but thank you all. In the middle, the funders, research doesn't come for free. Brackets some of it does in our lab if I have some spare time or if we have some good students. But we've been very fortunate to receive funding from UK research councils over the years and from the European Commission Framework 6 and Framework 7 projects for 2 very large projects on wave forces and wave overtopping. And we've also received EC money for access projects, so access to large facilities, the sorts of facilities that we don't have here anywhere in the UK, let alone at this university. So thank you to the funders, also to the Environment Agency who have supported our work, and also to the University of Edinburgh, and particularly to Cathy up in the very back row for allowing my extended overdraft arrangement at the Bank of Engineering, which I believe I will be clearing in the next weeks after several years. So thank you very much to the University of Edinburgh for... So we have the mentorship and the encouragement over on the right. Some of these people I've co-authored in other areas, others have just been around offering sage advice and moral support, and I'm deeply grateful to all of the people there. And right down at the bottom in the middle, the 3 amazing women in my life, Claire, Catherine and May, who are here, and also my sister Sarah is there, and she'll be up there as well. So thank you very much. Okay, so let's get down to some work. That didn't go forward. Here we go. So what's this all about? I thought I was nearly prepared at the end of last week, and then I bumped into Professor Hopgood in the corridor. Thank you, James. And James said, so what's your punchline? And I thought, oh no, I haven't got a punchline. So thanks, James. So I've got a punchline now. What does it all mean? We have a slide which I hope sets this into context. What's this all about? Why are we doing this work? My friend and colleague Aristides Kaprakis, who did the inaugural a couple of weeks ago, showed a terrifying slide of the record upon record of global temperatures being beaten month upon month upon month. So my terrifying slide is the NASA data there, top right, looking at global sea level, and that's very clear. The graph starts at 1995, which coincidentally is when I taught Fluid Mechanics 2 for the first time, and sea level has increased 100 millimeters since then globally. So that's pretty terrifying, because 1995 to me doesn't seem like that very long ago. And as we'll see later in the talk, 100 millimeters is quite a lot, because what happens at vertical walls when these waves are violently hitting them, the responses are very, very sensitive to the wave height, and they're very, very sensitive to the water depth. So the bigger waves can get in closer to structures on deeper water, and also if your structure is so high and the water has gone from here to here, your structure is not as high as it used to be relative to the water. So that's a big deal for us. And as you can see in the Nature technical report there, there's a real amplification effect with sea level rise and the responses of coastal defences. Down the bottom right, can the Dutch save the world? Well, the Dutch, of course, can save the world. But the point of putting that in here, the Dutch have been, it costs. The Dutch have been investing in coastal defence since the disastrous North Sea flood of the mid-50s. And they invest something in excess of 0.1 of their GDP, year on year, decade on decade. And we don't. And so yes, you can defend if you're prepared to pay for it. So one of the reasons for doing this work is to drive down uncertainty. Uncertainty is the enemy of costs in engineering. Having to manage large uncertainties drives costs only in one direction. And so if this work, and of myself and all of the colleagues, can drive down that uncertainty, that is a contribution. So that's the context slide. Hopefully, James, that's satisfactory. Thank you. We're going to now, if I can make this work, see what you think should be in a good inaugural lecture. This is where I first have to use the keyboard. So we do Alt-Tab, and we go to, where's the WooClap one going? This one. And hopefully we see what you said. So what have you said? You've said, oh, I must have put my own name in there dozens of times at the start, okay? Youngish-looking professor, fun. I started it off by putting short, but nobody's repeated that. One of my wonderful, amazing daughters put, don't have to wait 6 years. Thank you, May, for that. So what have we got? Clear sound, wine, committed to live a good, don't know, good, we'll know at the end. So that's fun. Focus on the future, yeah, good. Fantastic. And some jokes. Okay, So thanks for that. We'll capture that, and I don't know if I'm going to be able to adjust my talk dramatically, but there's some Gaelic in there as well, is there? Anyway, it's all moving around a bit. Anyway, thank you for that. That's great, and we've got to use this keyboard again to get back to where I was, which I think is this one here. And onwards we go. And I'm not going to do the second question because I'm desperately trying to finish sensibly on time. I was going to ask you what the coast meant to you, because for most people the coast means sand and beaches, or beautiful coastline walks, sun-drenched blue seas, blue sky, not a wave in sight. That's what you think about, isn't it? So by the end of today, I'm hoping that you see the coast in a slightly more exciting, challenging light of these giant waves. Now, it's traditional in these inaugurals to have a quote. We've been blessed by a couple of wonderful lectures by wonderful Greek colleagues recently, and of course, our Greek colleagues have got an amazing classical literature to draw upon for the very best of the quotes. So I thought I should put a quote in here, because that's what's done in these lectures. I don't know if you put that in your questionnaire return there. And so I would go to Robert Louis Stevenson, or Cousin Lewis, as we call him. Very fortunate to be first cousin 4 generations removed from Robert Louis Stevenson. So where else would I go for a quote? My first one there is one of my favourite RLS quotes that compromises the cheapest lawyer. I don't think we need that tonight, unless anybody's going to sue for dissatisfaction or if any of our designs are disastrously wrong. But I put that in there because everybody can use it in your life. The second one was new to me when I was looking for these quotes a couple of days ago. Everybody, sooner or late, sits down to a banquet of consequences. So that's pretty dark, isn't it? So I don't think we need that tonight, but I was so pleased to find that I thought I would share it. And the one that I really like is the big one. So I won't do PowerPoint karaoke, but do take a few moments to read that or look on catch up, because I think actually these days it's very difficult sometimes to look at yourself and feel valuable and feel valued. And I think it's a beautiful, beautiful quote that hopefully absolutely everybody in this room can read and feel that actually you are worth it, you are valuable. I changed it a little bit as well. I did think that there was probably a bit of, I'm sure RLS, of course, was from the amazing Stevenson family. I'm going to diverge and go over time. This is a disaster. I promised myself I wouldn't. But RLS was from the amazing Stevenson family. His father, his uncle, his grandfather were amazing maritime civil engineers. They built some of the most extraordinary lighthouses in the most exposed places. So Robert Louis was known as Louis in the family, and he changed his name as an affectation because he liked French. So he was born Louis. So Louis was meant to do engineering, and actually Louis students here, he was one of you. He was a civil engineering first year, twice as it happened. He was a civil engineering first year. He begged Professor Fleming-Jenkin to let him back in for another go, and he failed a second time. And then he went off to do law, and he went off to write. So he was not a great civil engineer, but he was a very extraordinary man. Okay. So it's the other, we're getting through, trying to gallop through the traditions of inaugurals. People put up wonderful maps of how they've trotted the globe around all sorts of amazing places, lived in amazing places and worked in amazing labs. So this is a very short slide for me. Okay. So we might zoom in a little bit here and zoom in a bit more. And the good thing about this is you can see I've actually lived in more than one house. So there's the journey, right? So it started up the top there at the Eastern General Hospital in Leith, hence my lifetime sentence to support Hibs Football Club. If you're born in Leith, you have absolutely no option. I went home to the then family home at Ulster Crescent in Meadowfield. Just under 2 years after that, and before my wonderful sister Sarah arrived. So her map is even less exciting than mine, actually. It's got one less stop. We moved to our family home in Duddingston. Then I became a student, and I broke away all the way to the new town because, as it happened, a family friend moved to the States for a few years and wanted somebody to look after the flat. So I lived in luxury in the new town. Then the bachelor pad in Viewforth Square in Brunsfield. And then along came Claire, and so we thought we'd better get down from a top floor tenement flat, and we have our little family home bungalow in the Shandon area of the city, which has been home to Catherine and May. We got there just in time before Catherine arrived. So that's the journey. In terms of my work, education, and professional life, it's even worse. So this is Duddingston Primary School. And Duddingston Primary School is not quite, but almost next to Portobello High School. And then there was the biggest jump in my life up to King's Buildings, also Blackfoot Hill. My undergraduate degree, well-kept secret, was actually in astrophysics. And I went on to do a master's in astronomical technology, which is where I got a little bit more of the engineering bug. So I moved, and after that, I moved down to King's Buildings to do work in water waves. When I was interviewed, and I've got a witness to this because Don Glass is here. Don was on my panel, so he's a lot to answer for. And so Don will witness this. The then Vice Dean of Faculty, Des Truman, lowered his glasses and said, "Looking at your CV, Tom, it appears your life has been lived in a straight line between Portobello and Blackfoot Hill." But the interview seemed to recover, and I think at that stage Des Truman had been in Edinburgh for about 45 years, so I think it was a completely unfair question. So there we go. So that's the life story bit. That was pretty easy. I have actually got outside Edinburgh in the rest of my life. I've been very fortunate in my work through conferences and also through student recruitment and student and university partnership building work to travel quite widely. I'm a little ashamed that I've never set foot on the amazing continent of Africa. That's certainly the next challenge. But I've been very lucky to travel pretty widely for work and also travel fairly widely for holidays. And you'll see the green dots and the yellow dots don't all match up. So I've not just been traveling at your student fees expense. You see most of these are proper family holidays. And as a nice, I missed pointing you to the two little RLS quotes. I think the RLS quote up the top, he was just 130 years ahead of his time in some ways. No foreign lands, it's a traveller only who is foreign. And to travel, there's better known one, to travel hopefully is a better thing than to arrive. Although we do like to arrive as well. And the final bit of the intro is that we like to usually have action man or action person. And so I don't get much time on the mountains, but I do love being on the mountains. So we sure do pictures on the mountains. My amazing family, and that's Claire's graduation from the Open University last September, which was the most fantastic occasion. Bachelor of Arts with distinction from the Open University in English Lit. So we're all incredibly proud of Mom. And down the bottom, the very cute Mark, not looking so cute in the bottom right with a whole bunch of fox poo on her, which took 2 washes, and thanks to May and to my sister Sarah for helping clean up the dog at the weekend. So how did I get here? I got here starting out doing work with Clive Gretted and Bill Eason and Dave Skyner, Matthew Griffiths, using a laser flow measurement system. So using a system called particle image velocimetry. And it was mostly applied to water flows, but we hadn't applied it to waves before. And I bumped into a gentleman called Hossein Omarachi, who was chair of coastal engineering at the University of Hanover at the time, on a visit there. Bumped into him in the staff room there, which we wouldn't believe how smoke-filled it was. And so he thought this would be an interesting thing to do, and lo and behold, it really was. So we did some of this PIV to look at what's actually going on under the waves as they steepen and come and smash into vertical walls. So it was really new at the time. You can see it was all done with a large format Hasselblad camera. And if you look very closely up here, my lab book on the 29th of June 1994 says darkroom mishap, ? Film 089 failed, repeat. So it was harder back then. If you got things wrong in the darkroom, you had to go back and do all the tests again. So that got me into this whole idea of waves and breakwaters. So finally, this is what we're going to do. I've been involved in a variety of bits of research. Been very honoured and very proud of being part of the Institute for Energy Systems when it was formed. And I've had a number of projects in marine energy. I'm still active in marine energy through our Industrial Doctoral Centre for Offshore Renewable Energy, supervising projects there and doing a little bit of the teaching there. I've been active indeed in hydropower a little bit, but I thought for today we should stick to one theme. So I'm going to try to stick to a road through violent waves at the coast. Okay, we could have done a bit some other things, but I'm going to stick to that because that's been the constant narrative through these 25 to 30 years. So we'll have a look at wave forces. So the forces on the structure, we'll have a look at wave overtopping, what goes over, and we'll have a look at hazard. So that's the plan for the next hopefully about 35 or 40 minutes. Why are we interested about wave forces? Well, you probably could answer that intuitively. Upper right is what's left of the harbour wall at Grève du Lac, which is on the island of Guernsey. It was one of a suite of so-called harbours of refuge that were put together by the Admiralty at times of tension with the French, and it didn't fare too well, as you can see. Middle right is what's left of the Wick breakwater. We mentioned the Stevensons before. This was a Stevenson project, and rather unusually, or possibly uniquely for a Stevenson project, it didn't turn out too well. So that's all that's left of the breakwater at Wick. And if you're interested in more of the historical stuff, I very warmly commend you towards William's PhD thesis. 10 years in the making, worth every minute. And an amazing look across historic failures through the lens of modern understanding of waves and the way in which breakwaters and seawalls behave. Down the middle at the bottom, something more recent. This is about 2009. This is a breakwater in the north of Spain, a wave energy breakwater in the north of Spain, and you can see it suffered quite catastrophic damage. We'll come back and say a little bit more about that later. And the diagram on the left has really stood the test of time. Any of the students among you, if you've got the time to draw a really nice diagram, do it, because you may still be using it in 30 or 35 years. So this was drawn by William in 1998, I think, and it's going into an EPSRC proposal as we speak, so it's had a good shelf life. Keep adding some arrows to it. So this tells you it's a complicated loading system. You would intuitively get the big orange arrow here, the horizontal wave force on the structure. You might guess that we might get this red splat, which is the breaking waves on the structure, the impact loads. You might also guess that we had some water going over the top, which could load the structure. Few of you would guess the right to left arrows, the seaward forces. We can get seaward forces due to a difference in the internal pressure in the structure to the pressure outside. And we can get seaward forces due to the way in which the wave is interacting with the front face of the structure. So we can get seaward forces as well as the landward forces. So we're going to take a little gallop through some of these over the next slides. I had intended not to include any photographs of anybody in the talk, but I really felt that I should put this one in for Clive. Because what we're about to do is use this little wonderful piece of apparatus that Clive, his research team, and the technician team over in physics put together many, many, many years ago. Clive's daughter is a lecturer at the Glasgow School of Art, and she and her dad put together a really special exhibition called Coast, bringing together science and engineering and art around the coast. And the centerpiece of it was, this is the great reveal, the centerpiece of it is this rather beautiful little wave channel. Everything is in perfect miniature, and the paddle is still in the right place, I hope. We will find out in a second. It looks pretty good, I think. So thanks, Clive, for putting this together, and thanks to Clive's family for pointing me in the direction, and thanks to colleagues Neil Wood and Jim Folek in physics for having looked after it so carefully and finding it and letting me borrow it for this talk. If you want to see Clive in action, you can search miniature wave tank on YouTube and you can get Clive's original commentary. So thanks, Clive, and we are thinking of you. Okay, so what I want to do then is play with this. With a bit of luck, if I put this behind and press the right buttons, we'll get a good view on the camera, which means those of you who've chosen to sit right at the back will still get a decent view. So hopefully that will go there. And if I press the right things here, that one, then we might have a magic wand. Well, hey, we do. This is where in class we zoom in on the sleepers. Which of course we don't have to do too much. So with a bit of luck, I will be able to run this and point this at the flume as a wand and let those of you further back actually see what's going on as well. So let's get it started and have a look what we see. So this is very complex. There's two buttons. There's one that says gentle wave and one says rough wave. So we should always start with the gentle wave. Talk to us afterwards about a wonderful German colleague who started with the rough wave. Not at this scale either, on something way bigger. So big that it's capable of blowing the roof off their flume room, which in fact it did. Allegedly, it was a storm, apparently. So what have we got? Let's see what we've got. If I go here, maybe you guys at the back can see the waves coming in. Okay, so we can have a think about what that's all doing. This is generating a wave at about a period of just under 1 second. So this is about 0.9 seconds. And you can see as the wave comes along here, it meets this foreshore slope, and it starts to steepen. Okay, so steepness of a wave is the ratio of its wave height to its wavelength. And as it starts to feel the bottom, its speed is going to go down. In the deepest water, and this isn't really even deep water here, in fully deep water, the wavelength is wholly dependent on the wave period. And in really shallow water, it loses its period dependence altogether, and it becomes only dependent on the water depth. And so the waves slow down in here, and the bottom takes its toll, and eventually the wave steepness gets to the point which nature can't sustain. It's too steep a front of the wave, and the wave will break onto the slope. And what it's doing there is plunging very gently onto the slope. We can put the rough wave on now, and let's see if we can see that from here. So it's doing much the same thing, it's just doing it a bit more quickly. And that's got a period of about 0.55 seconds. So what happens? And we could do a couple of lectures on this stuff. We can put in different slopes. We can look at different behaviors. But what we want to do here is we want to put in a vertical wall. Okay. So thank you very much, Andrew, for the vertical wall. The wonderful thing about tiny flumes is that everything is extremely quick and easy to do. It's quick and easy for Andrew to do, not for me. I'm sorry, Andrew, I was very disorganized. So if let's put the gentle wave in. And I'll put my wand over here again. If we put this little vertical wall in reasonably deep water, you can see that the water's running up and running down. The wand is in a good place. Okay, so that's what we might call a pulsating load. It's not terribly exciting, it's reasonably easily predicted. This is a very simple flume, so the wave energy is just being reflected back to the paddle, and it's reflected back off the paddle and coming back down. So, whereas in reality, the wave energy goes back out to sea. More sophisticated flumes, any serious scientific flume, the wave energy is reabsorbed at the paddle, so you don't get that build-up of energy. So if we put this in a little bit further up, we're going to see something rather similar. But if we happen to put it in where the wave is breaking, we're going to see something just a little bit different. I'll just start it again. I've allowed myself about 6 minutes for the demo, so I could get terribly carried away. So that's just a little wave breaking on there. You see it's a bit more violent. It's quite a lot more violent. And so the physical process is going on there at the wall. You can hear it. Yeah, so that's the little slap of the pocket of air hitting. So you're going to need a different set of rules to deal with that situation than you would in this situation, because the speeds are different, the timescales of the force, the pressure changes are different, and all sorts of different things are going on. You'll notice as well that if I stop it with the vertical wall in, it takes a while for the energy to dissipate, and if we let nature do its piece and dissipate on the beach, on the foreshore, it dissipates very quickly. We could do that with the rough wave, and we can see in reasonably deep water that we've got, again, pulsating loads, so slowly varying loads, but this time we've got some overtopping. Now I'm going to take it out before the standing wave builds up too much, because we don't have any absorption down here. If we go slightly shallower, same thing. But if we go to where it's breaking, we've got something quite different, okay? So you can see that just that change in water depth makes a really big difference to what we see. Right. So, let's take I could hide now, could hide behind here for the rest of, our photographer would kill me afterwards, or kill me during. Okay. So, here's one we did earlier, if I could press the correct buttons here and go back to the presentation. With a bit of luck, we can have a close-up view here. And of the fast one. What's more interesting is if we slow things, if we slow things down. So I said that research costs money. This was taken with my iPhone 8, which cost me £8.50 a month with Tesco. It's quite extraordinary. You guys who are working and a good deal younger don't realise this, but this would have been undreamed of. It would have cost a fortune to get a camera that produced anything like that. Risk of diversion again. Our first digital camera that we bought for PIV had a frame rate of 1 frame every 2 seconds. It came with a cooling unit. It had 4,000 pixels and it cost £25,000. So that's where and it was monochrome. That's where digital cameras have come since about 1993. So big changes. And there's the slowed down one. So you can see the wave. Now, this is not a really accurate representation because this is such small scale. In Fluid Mechanics 3, we used to do a piece on scaling. I think it's probably still in there. And waves scale beautifully down to lab scale to a very high degree because everything's dominated by the interplay of gravity and inertia. But when you get really small like this, then surface tension is unrealistically big. And so the surface tension effects in the very, very small flume make this a little bit unrealistic. Also, this is fresh water. The way in which bubbles behave in fresh water is different from seawater. And of course, the bubble doesn't know what size of wave it's in. And so the bubbles here are not behaving in a realistic way. But nevertheless, the overall kinematics are indicative of what we would see in a bigger flume or indeed in reality. And I think it gives you a nice sense of reality, seeing something almost tangible like that. I was going to do this bit later, but in the interest of time, I thought I'd put it all together. Andrew also made me a Dutch sea dike to go in here. I'm not going to put it in right now. I filmed it earlier. Actually, it's not really a Dutch sea dike because it's at a 1-in-2 slope, and nobody except the British would build a 1-in-2 slope because it's the worst case for wave overtopping. So this is not a Dutch sea dike, it's a good British sea dike. But we can see some different effects on there. So I did the same thing, I put that in, and we can see what to look for here is that we're getting a different type of braking. So there we had a little mini plunge, and here we've got waves that are really surging up the slope. And that's for the longer period wave. And if we put the shorter period wave in, we see the wave collapsing on the slope. And we can write a little spreadsheet that tells us what we expect and see if the type of interaction of the wave and the slope in the model is the same as what we expect in reality. So, I was going to do a bit of Excel Live. My students have probably fed up of Excel Live anyway, so we're not going to do it live because it was making me worry about the AV. So we do it almost live. Just to show you how things scale. This is our little flume here with a 0.9 second wave and a 0.55 second wave. And the way that scaling works is that if we have a scale of 10 to 1 in physical scale, geometric scale, then we have to scale the wave period by square root of that, so about 3. And so if we reckoned that this was a 10 to 1 scale model, then that would give us a 3-second wave and a 1.7 second wave. Still really tiny waves, so that doesn't kind of make much sense. So if we tried something bigger, if we tried a 1 to 50 model, if we imagined this was 1 to 50, that would give us a 6.5 second wave and a 4 second wave. So it's still pretty short. Those of you that spend time at the seaside, if you're down after a storm somewhere, even on the North Sea coast, the waves could be coming in every 8, 9, 10, possibly even 11 or 12 seconds. If you're on the Atlantic coast, certainly 11, 12, 13 seconds. So this is still rather short. So if we imagine 1 to 100 scale, we'd have a 9-second wave, and a 5.4 second wave, still quite short. And so I reckon that we're something like a 1 to 200 scale here, because that means that our slow wave, or not our slow wave, but our longer wave is equivalent to about a 13 second wave in reality, and our shorter wave is about a 7.5, 8 second wave. So those are quite interesting real waves to think about. We could spend a lot of time playing with the spreadsheet, and we won't do that. But scaling is a wonderful tool in the toolbox of fluid mechanics modelling, physical modelling of this type of system. So this is what we got when we put the wall in. I'm doing this just to make sure that people on Teams can see it. And so on the left is our pulsating loading, and on the right is our much more violent loading, what we might call an impact, or impacting conditions, or impulsive conditions. Okay. And we got the sound as well. This is jumping ahead in section 3, which we'll get to, I hope, in good time. We're interested in what happens to people on the structures. How you scale a person at very, very small scale is not really well nailed down. We know that the person's stability, or in this case, the small screw's stability, is a balancing act between how much friction is available between their feet and the surface on which they're standing, and the drag force of the water around their legs. Drag force goes as the area, the frontal area of their legs, so it goes as the square of a length scale, and it goes as the square of the speed. The available friction goes with the mass of the person, and so it should go as the cube of the geometric scaling. So we ought to be able to marry up, scale the person correctly such that their available friction is at the correct scale to the drag forces that are coming in from the water, due to the water rushing around their legs. I did this very, very roughly, and I reckon that the scaling should be somewhere between cubed and squared, depending on the wave speed coming in. And so I found something just under a 1 gram mass to represent a 60 kilogram person at 1 to 200 scale, squared and a bit. And we can see that I went through quite a few of these to try to get this just right, but we can see there we've got the drag force on the little person exceeding the available friction between the person's feet and the surface. So there we go. Off to safety, we hope. Okay, so let's scale this up one. So this was tiny scale. Let's scale it up to our lab scale, the little flume in the Sanderson building. And thanks, I think Tom was in the audience. I think Tom took these videos very, very long time ago. Still known as Young Tom, Tom Davey, now big boss of Flowwave, then possibly even my MN student or PhD student at the time. So this shows the slowly varying waves, what we might call green water overtopping and pulsating wave loading. If we look at the situation where the waves are breaking, we see this, and we see something a bit more realistic. The waves are better controlled. The scaling is a little bit less extreme. The influence of surface tension is probably much, much less of a concern. This is probably at a notional scale somewhere around 1 to 40, 1 to 60, 1 to 80. And then what about the last step up in reality? This is a very, very old movie, but I do love it because it shows you really nicely what happens in reality. When it runs, go on. It ran beautifully when we started. Let's just try one more time. Here we go. This movie is so old that they've entirely rebuilt the waterfront since this movie was made. But what you can see is that switch, okay? It's not a gradual change from not too impulsive to a bit more impulsive to very impulsive. It is this sudden change from nothing much to bang. It's just when that wave front just reaches just that right shape and interaction with the wall, and you get that very violent, that very impulsive type of interaction. What does it look like in the lab? Again, this is an old graph. This goes back to Proverbs Project days and Diego Vichinanza and Janice McKenna down at HR Wallingford. And if you put a pressure cell and look at what you see on the front face of the structure, you see lots of little ups and downs, these pulsating loads, but once in a while you see this bang, this very, very sudden impact load. And so you can see you really need to understand those in distinction to the slowly varying loads. We won't have time to drill into this too much, but there's a trade-off between the length of time that impact lasts and the intensity of that impact. So the very highest impact pressures or impact forces tend to stick around for the shortest time. That's very important because if you're impacting a wave on a very giant, many hundreds or thousands of tons of monolithic concrete caisson with sand fill, that's got a lot of inertia. And by the time it even thinks about moving, the force is gone. Whereas if you've got a structure with much smaller elements, maybe a crown wall or maybe like blockwork structures that we're coming onto, then the structure might have a chance to respond to that and it could be much, much more dangerous. Those doing fluid mechanics too will be used to the idea of if you've got two different regimes, you need two different sets of models, and you also need a discriminator. You need something to tell you which model to use. So the first thing that you come across in fluid mechanics is Reynolds experiment, and you need to know whether the flow is going to be laminar or turbulent, and so you use the Reynolds number. It's not quite as simple here, but we've got this wonderful parameter map put together by some familiar names under the Proverbs project, which tells you as an engineer the combination of your structure geometry, your water levels, and the wave conditions, what sort of loading to anticipate and to design for. So I mentioned Blockwork a few moments ago. This is where impacts could be really, really interesting. There's a lot of old coastal structures out there. A lot of old coastal structures, many of which don't have big money behind them, many of which protect ports of very little or no economic significance. They may not have, or almost certainly will not have experts around to monitor them, to assess their condition and to design repairs. So the examples there on the left is Arbroath, the roundhead at Arbroath, and you can see down here there's some, if you've been doing coastal engineering as long as I have, you can spot there's a missing block there. And you can see that there's been vernacular repairs done, attempts to bind together the blocks in all sorts of ways, with mortar, with grout, and with bars. So there's all sorts going on there. This is from the beautiful old pier at St Andrews. You can see the pier at St Andrews isn't straight. It's because at the time of the late 18th century, the engineers were choosing to follow the natural rock skerries to minimise the difficulties of building that pier. And again, you can see that there's a block missing here. That's a dry stone construction. It's open fronted. There's no grouting. There's no mortar between those blocks. That's designed that way as a dry stone. So what happens there when impacts happen? Well, this was some work on the right led by Gerald Muller, now then Queen's Belfast, now Southampton. And if Gerald, you're online, I'd love to see you up here sometime soon. And thanks for the great collaboration. What happens if your impact pressure here goes into a crack? Now, Gerald built a lab crack, and he instrumented it. And he watched what happened to a pressure pulse as it went into the crack. And the news was not good, because the pressure pulse propagated all the way to the back of the crack, which was quite some distance. And then it bounces off the back and doubles and comes back out again. So it's pretty bad news. It's the worst news you could have for pressure in a crack. And then Gerald put a right-angled bend, a 90-degree bend in his artificial crack, and the pressure hardly noticed it. It just went in and back out, just like it was a straight crack. So there's some fairly scary stuff there, which is subject to of a current research proposal that is being led by Alison Raby down at Plymouth, with some support from colleagues at Cork and Edinburgh, and also William. Blockwork closer to home. This is North Berwick Wall as it looks at the moment. Probably in fairness to say this probably wasn't a wave impact damage. This was a very unusually high sea level. There was a storm surge, there was a high tide on top of the storm surge, and there was also unusually high waves. North Berwick Harbour is actually fairly well protected, but the waves got in from just the angle that can give the biggest waves. And I think in this case, it's just been pushed over. But it's just a reminder that these things go wrong and costly. We'll be looking at something in excess of £1 million of work to get that back up and running. And on the right there, some lab tests conceived by William and conducted by Adrian Pearson down at HR Wallingford on failure of blockwork structures. Next step in wave forces is impulsive seaward forces. I'm not going to dwell on this because it's a niche, but I think it's a really rather lovely niche. It was an idea, I think, first brought forward to the Provost project by Jensje Vandermeer, who's with us this evening, and we went to test this in Edinburgh. This is what's called a low-crested breakwater. It's designed to let water over under the highest sea conditions. So it's a trade-off. It's going to cost less, but you're not going to protect your harbour for quite the same proportion of the time. And if the wave goes flying over the top, can it impact on the water on the seaward side, and the answer, on the landward side or the protected side? The answer was very, very much yes. This is a graph of the horizontal force, and 0 is here, and the stuff above 0 is the way that horizontal force you expect to go, which is towards the land. And you see this great big spike down there. So a very large impulsive horizontal seaward force as that jet impacts the water behind the structure, trapping the air in that. So this was it's a niche, but I thought I would like to share that because I think it was a rather beautiful little piece of work. What about downfall pressures? Diagram top right is a beautiful diagram from a very early text on coastal engineering by Shield from 1895, and basically it says what goes up must come down. But actually, if you went to the guidance, you would find very little to tell you what forces are involved when the stuff does come down. And so, together with colleagues at University of Rome, Tre, Leopoldo Franco, and Paolo Alberti, we conducted some small-scale experiments here in Edinburgh. And then Gerald and colleagues did similar things with larger-scale tests in a very large flume in Germany. And what we found was that the downfall pressures here, the largest downfall pressures could be of the same order of magnitude as the largest pressures on the front. So these are huge pressures. I did waste about an hour of my preparation time trying to find an old photograph I took at Peterhead North Breakwater. We coastal engineers really know how to live. We live our life on industrial ports on breakwaters. Because a manhole cover had been dished by downfall. So a manhole cover had been bent down, and by measuring the dimensions of the this is a test for the structurals in the front here, measuring the deflection down of the manhole cover with knowledge of the thickness of the cover and the dimensions of the cover, you can work out what, and ROAC's formulas for stress and strain, you can work out what the force must have been to create that. And actually the force is in very good agreement with what the lab tests would have suggested. So I wanted to show you my really sad photograph of a dished manhole cover on Peterhead North Breakwater, and I couldn't find it, unfortunately. But that was a nice piece of work, and I think very helpful. And just before we leave wave forces, a look across where coastal structures meet wave energy. The oscillating water column is a class of wave energy structure built at the coast. To me, it's possibly the most, one of the most interesting types of wave energy device because it's relatively simple. The devil is in the detail, of course, but the concept is simple. The maintenance is potentially simple because it's at the coastline or close to the coastline. And, but it is, in fact, a very complex loading system. The idea there is that the waves run up and down on the outside of the structure, and the changes in pressure here drive a column of water up and down within that chamber, which in turn drives out and back in the air out of and into the chamber through a turbine generating electricity. But it's actually a very complicated loading system. That's witnessed by what went wrong at Mutriku. So there's a picture up top right of how Mutriku Harbour looks now. Bruce family, funnily enough, found themselves in Mutriku en route to holiday house in Spain. I don't know how that happened, guys. I'm sorry about that, but we found ourselves with one of the world's most interesting wave power stations. This is a beautiful little village on the Basque coast of the north of Spain. So this is a conventional rubble mound, but this bit in the middle here is the wave power station. It's 16 chambers of 20 kilowatt generators. So it looks beautiful now, and it's working very well now. But this is how it looked during construction, because it was hit by the design storm during construction. And you can see that we're not going to generate much energy when the chamber is open to the wide world, as it was there. Bit of forensic engineering there. You can't see too clearly in the picture, but the reinforcing bar that has been broken as the concrete structure exited is bent outwards and not inwards. So that structure exited seawards and not landwards due to pressures within the structure. So it blew out rather than blew in. I don't really have time to tell you the story of Shada, but this was the wave power station which was never to be on the northwest coast of the Isle of Lewis. So a fantastic wave power site exposed to the Atlantic looking across to Canada. Originally conceived as a 4 megawatt station and eventually uprated to a 20 megawatt station, and eventually, unfortunately, didn't come into fruition due to delays in the ability to remove large quantities of electricity across the Minch to the mainland. So that is unfortunately no more. So this is a complex loading system. We might have pulsating loads on the outside. We might have impact loads on the outside. We might have downfall pressures. We'll certainly have pulsating loads on the back wall of the chamber. We might well have impact loads on the back wall of the chamber. We might even have slam loads on the ceiling of the chamber. So a really complicated system. I reckon I have a good idea about once a decade. So my good idea for the 2010s was to request a camera to be put inside the chamber of some very large-scale tests that the European Commission Hydrolab project very kindly gave us time to test in this giant wave flume in Germany. So what you see there is up at the top there is what happens if you close the exit to the chamber. So no air can get in and out. So that's no use for generating energy, but it's rather beautiful because you can see the pressures rising and falling. You can see the vapor pressure being reached at the low pressure end, and you can see the condensation coming and going. And that's in real time. Down below is this beautiful situation of an oscillating water column working just as the textbook would say, column rising and falling rather beautifully and generating lots of energy just exactly as you calculated. Things get a little bit different in reality. We find that you may get a little bit of sloshing. You might get quite a lot of sloshing, and you might get really big problems. And this was a topic of my fantastic Indonesian PhD student, Krishna Adi Poetan. Krishna's via Japan is now at Princeton. His map would be much more interesting than mine, and he's only 28 years old or something. But anyway, thanks, Krishna, for the amazing work on that, and thanks to co-authors also and colleagues who participated in the tests in Germany from University of Naples, from HR Wallingford, and Allsop Consulting. And I'm not going to dwell on the scaling, but this scales. Another part of Krishna's PhD was to work out how you can scale this, because OWCs have got air and water all going on at the same time, and that's very, very challenging for scaling. But Krishna came up with a way that we could use small-scale models, a bit bigger than what I've got here, but about this size in our flume over in the Sanderson building, to investigate these effects very effectively at small scale, which is cheap and quick. So phase 2, and I'm not too far behind schedule, phase 2 is wave overtopping. Why are we interested in wave overtopping? Well, there's certainly at least three reasons. One is for flooding. If a wave comes over your defence, it may cause flooding backshore. And to predict the levels of flooding or to decide how much overtopping we can allow, we need to know a mean. We just need to know a time average of the overtopping. We usually call that discharge Q. We might be interested in wave transmission. This middle picture here, that's not the opening to the harbour. Okay, that's waves going over the top of the wall. And so there's a lot of agitation in the harbour there, and so we need to work out what overtopping we can allow to limit agitation in the harbour in amount and also in frequency of occurrence. And so we need a mean discharge there. We might also be interested in individual wave overtopping discharges because it's the individual wave that will batter your expensive boat if it's moored just behind the harbour wall. And down at the bottom of this picture from a recent study by Yenchi, we'll come back to the study in a few minutes from now, we're interested in direct hazard to people. And for that, we need to know the individual volume, wave by wave by wave, not the time average. And actually even better, we'd like to know what the fluid's doing around people's feet. What's the flow speed and what's the flow depth? So that's the three reasons to be interested in wave overtopping. In overtopping, you see lots and lots and lots of graphs like this. So this is a graph of the overtopping, the mean overtopping, so the time averaged overtopping on the y-axis, plotted against the relative freeboard on the x-axis. So what we mean by the relative freeboard is the height of the crest of the structure compared to the still water level relative to the height of the wave. Okay, so it's divided by the wave height. So you could have, for a given relative freeboard of 2, you could have a higher structure with bigger waves or a smaller structure with smaller waves. So there's quite a bit of unpicking to do in these graphs, and I don't have time to do it all, but there's some interesting reading here. First of all, let's look at the two straight lines. These are long-established lines. Williams' line from 1995 and Leopoldo Franco. I don't know if Leo's online. Leo, if you're online, very sorry you're not here. I can't wait to see you in Rome at the conference in September. So these two lines, William better cover his ears, but William's quite reliable, and Leo is also very reliable. So who was right? And it actually took till about 2010 for Jensi, who's in the audience, to really get back to the detail of what was in those tests to work out who was right and who was wrong. And the very happy outcome was they're both right. But the situations were slightly and subtly different. And Leo's line was for situations where there was not an influence of the foreshore, like we've had in our model here, whereas Williams' lines were for situations where there was an influencing foreshore, like we do have there. So those lines are both right. But those are for pulsating loads, for pulsating waves, for these slower varying waves, these green water overtopping, not for the impulsive waves, not for the breaking waves. But for those ones here, you can see that there's as we increase the freeboard, the height of the structure, we have an exponential decay of the overtopping. So this is a log scale on the y-axis. Now that's important because if you read that the other way, if your wave height gets a little bit bigger, your overtopping gets a lot bigger because it's a log scale. Or if you want to maintain, if your water level goes up, you move this way as well because your freeboard goes down. Your water level goes high, your crest stays the same, so your freeboard goes down, so you move this way. So a little change in water level can give you a big change in overtopping. So it's a very, very sensitive system. That log scale is super, super important there. The other thing to look on this really interesting graph, and I'm sorry, the students are used to me getting overexcited about graphs, is these lines here. This is a collection of conditions where the waves are breaking. These are impulsive loads, so we've got bang, bang here. And as you can see from what we saw in front of us and from the videos, the water can leap up a lot higher. And so actually building higher and higher is less and less useful when you've got impacting waves. Now the Japanese take a very simple approach to this. They just build their breakwaters where you can't get impacting waves. They build them in 60, 70, 80 meters of water. That's expensive. It works really well, but it's not the approach that's been taken very widely. So we in the UK and widely in Europe are in these situations, and we need tools to be able to accurately predict the overtopping and the impacts of changes. One of the earliest projects, the first big overtopping project I was involved in was a UK project called VOWS, Violent Overtopping by Waves at Seawalls. It was led actually out of Edinburgh with collaboration with HR Wallingford. And there's this line here was due to Phil Besley. So Phil was taken from us far too young 8 years ago now, 9 years ago. Phil was my external examiner. So we miss you, Phil, very much. This was Phil's line from HR Wallingford tests, quite a substantial set of tests, but we set about a very, very large parametric survey of tests of overtopping under these breaking wave conditions. And we couldn't break Phil's line, but we were able to augment it and corroborate it very, very successfully. So that's small scale. A recurring theme of this evening is scale, right? So what do you do after you've done the small scale? You do the small scale first because it's cheap. It's easy. This is micro scale. You wouldn't do this because it's probably not accurate. But in the lab, we're pretty good. But you do want to go up a step to large scale. So we were very, very fortunate to win 12 weeks of project time in a very large wave channel in Barcelona. I'd actually wanted us to get into the channel in Germany, and I was slightly disappointed when we got to Barcelona, and my colleague William said, don't be ridiculous, this will be much more fun. And I think he was right, and it was a wonderful place to work, and a wonderful team at the lab there at the University Politècnica Catalunya, who supported our work there. So these are much, much bigger waves. I don't have a person in there, so you can't see the scale, but these are much, much bigger waves. And so we wanted to see how we were getting on scaling. So we set the tests up to be as close as possible to our small-scale tests. So our breakwater was about so high, and this breakwater was more like sort of so high. So big jump up in scale. And actually, we got remarkable agreement. I didn't expect such good agreement because the white water flying through the air shouldn't scale terribly well. But the mass of water that goes over does scale very well, and obviously the wave kinematics up to that point seem to scale very well because the large-scale tests are the black ones here and the small-scale tests are the white ones. So we got really, really good scale results. And over on the right, we won't go into that, but these are the individual wave volumes. Remember, I said sometimes we're interested in the actual volumes of individual events, and actually they scaled very well too between the small-scale tests at Edinburgh and the large-scale tests in Barcelona. And the last step in the journey of getting robust engineering guidance, going from small-scale to large-scale, is to go to the field. Field studies are notoriously difficult. Nature tends to give you the mildest winter and the gentlest winter on record if you've gone to great trouble to put expensive equipment out at the coast. And this was work done by colleagues H.R. Wallingford in collaboration with the University of Edinburgh, looking at wave overtopping at this vertical wall here on the south coast of England. This is a Samphire Hoe site. It's a reclamation from spoil from the Channel Tunnel. It looks very bald there. It's now beautiful and green, and it's a country park. And they set up these wave overtopping measuring devices on the crown deck of the breakwater there. And while there's a fair bit of scatter, nevertheless, the level of agreement is very encouraging between the line derived from small-scale tests, tested further in large-scale tests, and then eventually looked at in the field. I really don't have time to do this one today, but I was good. Very rarely do I, as an academic, get to do some consultancy. We had a lovely piece of consultancy brought our way by Jensi from the town of Harlingen in the northern part of the Netherlands, who were doing improving their 1 to 10,000 year sea defences and looking at using quite novel structures to do that. And we had a wonderful visit from some of the seniors of the town of Harlingen, and we viewed the tests, and we had, if I remember correctly, a fantastic haggis, neeps and tatties supper in my old bachelor flat in Brunsfield with a group of about 10 or 12 wonderful Dutch colleagues. And I'm not going to do this one now. This one brings us right up to date. Jensi, Leopoldo, and myself are involved in trying to push the limits here. The previous graphs I showed you had relative freeboards of up to about 3 or 4, and we've just taken it to extreme. We're extreme coastal engineers, and we're taking these extremely high structures up to relative freeboards of 9, 10, even towards 11, looking at how waves can get over the highest of high jumps there. That could be important when you're designing where you really need extraordinarily low wave overtopping. And we're not going to do the video because time is a little bit against us. As the last slide on overtopping is to say, well, what's the point of all of this? And I'm very, very privileged to have been part of a huge team which brought together this largely European research on wave overtopping. We focus today on vertical structures, but there's a whole lot going on sloping dikes, on rubble mound structures, armoured structures, and so on. And very privileged to be part of the team that brought together the outputs of a decade and a half of European research and European-funded research to practice. First of all, in 2007, with the publication of the first European overtopping manual, and again in 2018, with the second edition of the overtopping manual. So I took a lead on the chapter on vertical structures. We have a couple of other lead authors in the room, Willem Alsop and Jensi van der Meer. In fact, Jensi really was the driving force on the second edition of Eurotop. So I'm very privileged to have been part of that team, and I think this has had a real impact, excuse the pun, on the community. It's also done me a great service because my Google H-index survives my spending too much time as Dean International and too little time applying for grants. Cover your ears, my bosses. Well, one boss will be happy and the other boss won't be happy. But this manual gets highly referenced, highly cited, so it keeps my nose clean in citation land. So finally, the final phase of the talk, I'm sorry I have just a few minutes over, is to look at direct hazard. If you look at the chart there, that's what you had as an engineer to design your structure until the mid-noughties, really. You had a chart that said if you're designing for pedestrians, if you go up here, the vertical wall becomes dangerous at about 0.03 litres per metre, litres per second per metre. And so you have to design your crest level to limit the overtopping to that admissible, that so-called admissible or tolerable overtopping. And it's actually just about, and the real engineers in the audience may contradict me, but it's just about the single most important parameter of design of a coastal structure is how high you build it. And it's also very closely linked to cost. The only thing that is more linked to cost is how long it is, and that's often defined for you. So that height is a crucial defining aspect of the design of a coastal defence. And it was based upon a mean overtopping. Way back in the mid-90s, it was realised already that that wasn't enough. This is a picture of a young Leopoldo Franco, wetsuited up, allowing his graduate students to loose off quantities of water at him to find out how much it took to knock him over. Now, Leo's very fit. I mean, Leo's one of Italy's top 10, top 20 over 60s tennis players. We could go on a terrible tangent and tell you about the North Europe versus South Europe five-a-side football we played in one of these European projects. And North Europe took an early lead of 1-0, and the final score was 13-1. Despite the efforts of our veritable Dane in the ranks. So Leo was an amazing footballer as well, as were a whole bunch of these young postdocs that were on the team. So Leo was very brave there, and he gave us also, I think, one of the best journal paper figure captions ever, which was assessing the first author's stability. So we knew then that it wasn't just about mean overtopping, it was about these volumes, but we didn't know what was admissible. So things moved on a lot through the Proverbs project, through the Clash project, European project, through a work package led by William on hazard, and onwards into the European overtopping manual, first and second editions. And so now you see that the limits based upon individual wave volumes are given. And hand in hand with that are better techniques to predict those volumes. So you can't just say, well, you have to limit it to 600 litres per metre and not tell you how. So we need better techniques to actually predict those volumes. And those techniques are pretty good now. So this is now part of guidance, but it's still not the whole story. As the whole story comes back to what we saw earlier, which is it's actually the water rushing around your ankles that knocks you over. It's not the volume that knocks you over, it's the speed and the depth of the water. So it's the drag force on your legs versus the available friction between your feet and the ground. It's not much more to it than that. So that's a very small scale study. There's actually been quite a lot of studies of this, dating back to the 80s, in fact. And you can see there pictures from some American tests in a channel there, some Finnish tests, again, in a channel, and some really pioneering tests at the very, very large wave channel in the Netherlands, the Delta Flume. You see what they've all got in common. They're all wearing harnesses, okay? Now, if you see the video of the Delta Flume one, I think this guy is scared. It's a bloody big flume. Sorry, you have to bleep that out. It's a very, very big flume. So I think he is a little bit scared, but these guys are not scared. These are graduate students. They're highly competitive, and they get multiple goes to try and do better than their mates. Okay? So they're having a fantastic time. And this guy's not too scared. There was a British piece of work which actually employed a professional stunt person to do it, so they weren't scared either. So those are great tests, so don't misunderstand me. Those are seminal tests and part of the literature of immense importance. But there's limits. I'm applying my critique to that. There's limits. They're fantastic tests, but there's limits. If you plot all of those, you get a cluster like that. So this is we did the overtopping graph. This is a stability graph, and so you see depth on the y-axis, and you see flow speed on the x-axis. And the lines you see are from a very simple model. I can't remember if this came up in the Fluid Mechanics 2 exam paper not too long ago, but basically it is just that model of the drag of the water around your legs. So half CD rho A squared, as you'll all remember. So half CD rho A U squared, as you'll remember correctly, versus the friction, which is just your normal reaction times the friction coefficient. Okay, it's as simple as that, almost as simple as that. And so those are the models. There's a model for where you might get pushed over, but that's for deep water. That's when the moment applied to you by the water exceeds the righting moment that you can apply by doing this or something like that, okay? But actually in the shallow conditions, the moment instability is not important. It's the water rushing around your ankles and your calves that is important. And so these lines here are very simple analytical or theoretical models based around those very simple concepts. And what we see is that the lines agree quite well with the data that's been measured in the lab. But the data kind of stops here. So this is where my MPhil student Claudio Sandoval kicked in. We've talked about lab tests already, and the next step after lab tests is to go to the field. So how do you go to the field to look at overtopping hazard? Well, Claudio went to the YouTube resource to look at real accidents. You can see I've put up in yellow, orange at the top, there's no fatalities. We actually genuinely worked quite hard to check that there were no fatalities in this, because it's quite gruesome. And we really believe, to the best of our knowledge, there were no fatalities in this. The eagle-eyed among you will notice this is not a wave, it's actually a tidal bore in an estuary. But my thesis is that it's the speed and the depth that's knocking you over. It doesn't really matter where that speed and depth came from. And so Claudio looked at this video and analysed the people as they went down, and from the video could estimate the speed and the depth of the flow at the point where they went down. So we'll let you see this. Look away now if you're squeamish. It's also quite loud, I think, so if you... so let's see. Probably seen, oh, we're stuck on loop. You've probably seen enough of that. It's interesting to note in passing that once people are down, they really go, because the coefficient of friction, dynamic friction, is always less than static friction. So once they're down, they're away. Here's a second clip that Claudio analysed.
So we can get yeah. We're going to continue to have the waves here today. We're going to continue to have the winds as well. In fact, this hour we're seeing a wind gust of 45 miles per hour at Gary. So even though both of our airports seeing wind gusts in the 20 mile per hour.
Oh!
That,
oh, no!
Oh, no! That is not good.
Spoiler alert, happy ending.
He's right at the edge there.
He's getting his...
There's his right at the edge. You know, and we're obviously at the point now. You know, we're at the point now. Yeah.
So, lesson for this evening, don't chase your bicycle over the edge of a breakwater either, okay? Let the bike go. Insure your bike and let it go. And the third clip was this one here, which was at a surfing competition at Mavericks Beach, California. And what's really touching there is the levels of sympathy from the crowd. So we don't believe anybody was seriously damaged in that, but again, it gave Claudio some much needed genuine field data. So you've got the element of surprise, which is absent in the lab. You've got the element of fear, which is absent in the lab, and we've got some quite good quantitative data. And when that is plotted, really rather delightfully, it filled that great big gap. It turned out to be all to the left, to the right on that graph of where the previous studies had been. The previous studies had been conceived and funded looking at the risks of fluvial flooding, river flooding. And so the depths were higher, the speeds were slower. Here we've got situations where you've got really high speed, shallow flows. It's the same axes, the depth and the speed, and the red markers are where people went down, the black markers are where people stayed up, and the lower theoretical line is the one to look at. That's the most critical one. And you can see that actually it seems to work really, really well. This person stayed up, but that was their second attempt. They'd already gone down, so they kind of saw it coming. So this is very encouraging. And just to bring things bang up to date before I close, some tests done by Jentje and Dutch colleagues on a dike in the Netherlands. The fluid mechanics 2, you'll get a cold sweat looking at that yellow box, because it's frequently appeared in examination papers in all sorts of guises. That is Jentje's overtopping simulator, and it's been very handy for a number of exam questions over the years. So what it's doing here is it's loosing off controlled volumes of water down this slope. Now you might say this is not quite the same as is real, because you haven't got surprise and you've not got fear. But what these tests have got is full scale and amazing instrumentation. So we're making pretty good guesses at speeds and depths from the video, but this is spot on. So these are really, really valuable tests. And you can see some stills from the pictures there. And happily, for our friendship, Jentje, the results came out very close to what we had found from the video and what we'd extrapolated from previous tests. And Jentje, being a much more practical engineer than I am, decided that for practical purposes, and probably quite correctly, for practical purposes, a good straight line would do there. And so we have, for the first time, some guidance based upon flow speeds and flow depths. So that's where we're at. It's a very exciting point to be. We're not going to do the woo clap again. I was going to see if you changed your view of the coast. So I'm going to close with this video, and thanks to Gerald for sharing this video with me some years ago. This is situations not yet considered. So we can say he jumped before he was pushed, or they jumped before they were pushed. And happily, in a few seconds, they reappear there. So you can go to bed in the knowledge that they're safe and still out there being dangerous. So just to conclude then, we need a punchline. We're trying to reduce uncertainties, and it's an opportunity to make the best of the resources we have in an era of climate change, with ever greater demands on the coast, ever greater economic development, and ever greater challenges from the environment. So this is important stuff in that respect. Collaboration is great. Conclusion number 2, I wouldn't be anywhere close to where I am without amazing collaborators, and it's been the joy of my professional life to work with collaborators across Europe in developing some of these models and these tools. My conclusion number 3 is that physical modelling is still essential. It's a fantastic tool. It's still a crucial tool. But David would probably actually agree with that, but David Ingram is up in, is it next week or 2 weeks, David? 2 weeks' time, and David is among the list of wonderful collaborators that we've worked with over the years, David has some extraordinary expertise in computational fluid dynamics, which he'll share with us. So what about next? Well, there's a lot more to be learned about blockwork walls, ever more at risk, ever more neglected. We need to improve our knowledge of the direct hazard to other structures, to vertical wall structures. We might be interested in infragravity waves, and we certainly need to think how we can restrain the person on the previous slide from getting within about 2 kilometres of the coast again. So I think with that, sorry I've run over time, but thank you very much for your attention. Thank you. Thank you.
Okay, I would like to thank Tom again. First of all, I'm going to just go off message for one moment. This was incredibly interesting, and I found as the mixture of the modelling and the understanding, but then the physical part of it, very, very interesting. I wanted to say, however, the thing which Tom hasn't mentioned, but is kind of obvious from the room as well, is the way in which he engages with people that's had a really strong effect for a very, very long time amongst the engineers here, but also for the university and all of the stuff that you do as the Dean of International as well, where you just flood the room with warmth. So thank you very much indeed. Right. So I want us all to thank Tom again for everything that he's done, for the work that he does, and then I want you all to promise that when you go out, chat with Tom, enjoy the drinks, please do not overtop your glasses. Thank you.
Very good. Thank you. Thank you. Thanks. Very good. Thanks.